Good morning. I'm gonna give a couple of you a greeting as you come into the room today. So good morning to you, Dr. Cockcroft, and good morning to you, Gunman. Good morning, Seabass. Good morning, Callie. Good morning, Annie Banani. How are we doing today? The Schuster twins. I still can't tell you apart even online. I don't know when I'm gonna figure that out. Good morning to Yoda. Good morning to Robbie, and good morning to, boy, I could say good morning to so many people today. Good morning to Zach, and I'll be calling on some of the rest of you during the hour too. So have a good morning. Today's topic is 5.6. Let me get my bangs on my face. They always seem to fall on my face because you know what happened? I'd say about a month ago, I was like round brushing my hair really hard and it tore out a piece of my bangs. So I've been having bang issues for like a month, and you know what? I don't like them. Speaking of that, good morning, Eric Lindgren. I bet you're having no shave April, aren't you? See, you can't even get away from me making fun of you long distance. So anyway, good morning. Today's topic is 5.6. So this will be done on a blank sheet of paper by you. You'll take a picture and submit that to me in Schoology just to make sure you're taking those notes, right? Well, actually, forget it. You don't even need to do, yeah, I'm going to make you submit them. I was going to say you could just learn it off of Delta Math maybe, but I think I want to see these notes. So they're not going to be particularly long or particularly involved. So let me begin here. Let me see what examples I'm going to do. I had to pre-write some down for you. All right, here we go. So 5.6, and you should be taking these notes on something, right? Preferably in a notebook, and you just sort of save those. I'm not going to be having a note packet available for you here long distance, and a lot of you don't have printers either, so that's okay. So for 5.6, what we're going to have is the derivative, and it's was in chapter 5. We quit at 5.5 because otherwise, we would have had to have a 2-day test. So this is tested very lightly on the AP exam. So I think what I'd like you to do here is write derivatives of inverse trig functions. So just a little brief recap on what the inverse trig functions are. We have sine of x, we have cosine x, we have tangent x, we have secant, we have cotangent, cosecant. We're going to focus only on these three. I'm going to turn my computer a little bit here. And their inverses are called sine inverse of x. And like any inverse, it undoes the original function. We have those are called the inverse functions, but we also write them as arc sine of x, arc cosine of x, and arc tangent of x. And Christian, if I were to ask you, why would we be calling them arc cosine instead of cosine inverse? My guess is what he would say is that because cosine inverse could be confused with the reciprocal of cosine, or 1 over cosine, which is secant. So we oftentimes will use these guys over here the most. And you might say, well, LaRude, what about the other three? In normal circumstances, we discuss the other three, but I'm trying to save some time. The other three we work with in a similar fashion, so it's just more you'd need to memorize. So I'm focusing on these three because these two are the only ones on the AP exam, and this one is so closely linked to that one. So go ahead and star those, and those are the ones you need to know, and in the Delta Math assignment, those are the ones that are exclusively asked for, so that's nice. I think, they might do cosine too, so in there. Have your notes out for all of it. All right, so let's go take a look here. I'm going to draw a little line, and first of all, let's discuss, well, what do these trig functions actually mean? What does it mean to take the inverse? So if I were to ask you, what's arc tangent of 1? Understand what that's asking you for. It's asking you to go in reverse. The tangent of what is 1? And you might say, that doesn't make sense to me. Well, let's say then that this is equal to y. To undo arctan, like to undo a square, we square root. So when I apply the inverse function to both sides, because these are inverse, it's like squaring a square root or doing e to the natural log, and I get 1 is equal to the tangent of y. So notice I'm looking for the tangent of what equals 1. All right, so you're looking for the angle. When you do tangent of pi fourths, you get 1. When you do arctangent of 1, you get pi fourths. So y would have to equal pi over 4. And again, these require a pretty good understanding of the unit circle, so let's review that for the gazillionth time. Remember, the reason why the tangent of pi fourths is 1 is because its sine and its cosine are the same there. So when we do sine over cosine, since both of them are root 2 halves, when we do sine over cosine, we get 1. So we say the tangent of pi over 4 is equal to 1, whereas the arctangent of 1 is equal to pi fourths. A really common one in using a new whiteboard here, a really common one that you'll see in Calc 2 quite a bit, because we work with infinity so often, so go ahead and draw yourself another line. What we see a lot in there is, well, what's the arctan of infinity? And you have to think about what that's asking you for. The tangent of what angle is infinity? Now, there's two ways you can think of that, but the easiest way to think about it is with the actual graph of the tangent function. Remember that tangent of 0 is 0, because it's its sine over cosine. And at 0, sine is 0, cosine is 1. For the tangent of pi halves, we would do its sine, which is 0, over its cosine, which is 1. 0 over, sorry, the other way around. We would do its sine over its cosine, which is 1 over 0. We say that's infinity because how many zeros can you fit into 1? An infinite amount. Or we also will say that tangent has asymptotes at the pi halves because tangent of pi halves is sine pi halves over cosine pi halves, right? And this is 0. So revisit our tangent graph from from pre-calc. So the question is, which angle has a tangent going to infinity? And then that would be on its principal domain, like from negative pi halves to pi halves. And the answer to that would be pi over 2. So that was just a quick little review of some pre-calc there. Not actually super important for what we're going to be doing today, but it's always good to review that, right? And get my picture out of there. So let's go take a look here. My goal is to figure out what the derivative is of, and let's start with tangent. My goal is, what is the derivative with respect to x of our newest function? Let's call it arctan, and let's say u. And remember, u in this class always stands for a function of x. All right, so my goal is to figure out, well, what is the derivative? I could just tell you, but when I think you can understand the derivation of the models, I like to show it to you. Will I have you derive? No. Will College Board? No. Will they have you use it? Yes. So let's take a look at a couple that we already know. Just again, we do lots of review right now. If I said, what's the derivative with respect to x of e to the u? We've had that one before. We say you do e to the u times du dx, or u prime. If I were to say, what's the derivative with respect to x of the natural log of u? We say you do 1 over u times du dx, or equivalently u prime over u. Again, we've done these, we've derived them, you should have them memorized. But if I were to say, what's the derivative with respect to x of arctan u, you'd be going, I have no clue. We don't know arctan. So all that I'm going to do right here is define arctan as y. So really what I'm looking for now is dy dx. I have no clue what the derivative of arctan is, but I do know what the derivative of tangent is. So if I could just get rid of the inverse, right, I would know the derivative. So what I'm going to do is take the tangent of both sides. Beauty of math. You can always do that same thing to both sides. Now, tangent undoes arctangent. Arctangent undoes tangent. It's like squaring undoes a square root, and square rooting undoes squaring. They're inverse functions. So these two undo each other, leaving just u on the right. And remember, use some function of x. If this was arctan of 8x, I just have an 8x on the right. And on the left, I have the tangent of y. Now, I know the derivative of tangent. The derivative with respect to x of tangent will have to be the derivative with respect to x of u. The derivative of tangent x is secant squared x. It's really secant squared x times dx dx, but that's 1. So this is going to be secant squared y times dy dx. And du dx we'll call u prime. And we could call dy dx y prime as well. I wish this had a scroll feature. I'm trying out a new whiteboard. I actually think I like my other one better, but that's okay. All right, so back to here. What I actually am here, I'm working on my iPad. Hi, guys. All right, hello, bowl. So next one, what do I do to solve this for dy dx? Whoops, I need to activate my pen and not my eraser. So if I were to say, hey, Jake, yeah, I see you there, Jake. What do I do to solve this for dy dx? You should say divide by secant squared. So let's go do that. Let's divide by secant squared. Now, right now, this is a big mess because we're like, well, what's going on here? But I'm going to go back to what I wrote right here when I had the tangent of, before I took the derivative, I had the tangent of y is equal to u. What does that tell me in this scenario? Y is an angle whose tangent, opposite over adjacent, is u, which means this would have to be a u and adjacent would have to be a 1. Probably should have drawn that right at that step, but that's okay. I'm not going to redo it. So again, I'm going to repeat. At this step right here, I ended up with tangent y in the blue box. When I did the tangent of the arctangent, I just got u. So I was sitting there with tangent y equals u. Well, tangent of an angle is equal to the opposite over adjacent. I'm also now going to go get the hypotenuse on this reference right triangle. A squared plus b squared equals c squared. So u squared plus 1 squared has to equal that c squared. So my hypotenuse is, to undo a square, we square root. It's a square root of, and I'm going to write it as 1 plus u squared. All right, in that triangle, that should make sense with our Pythagorean relationships. So back over to here. I have dy dx equals u prime over secant squared. Well, these need to be functions of x. Keep in mind, u prime will be, if u was 8x, u prime is 8. All right? Secant squared y, what would that be in terms of u? Well, cosine is adjacent over hypotenuse. So secant will be hypotenuse over adjacent. It's the reciprocal, lots of pre-calc in here. So when I square it, I would have hypotenuse squared over adjacent squared. So back up to the top here, if I do my hypotenuse squared, right? So I have the u prime on the top. And on the bottom, I'll have the hypotenuse squared, which is the square root of u plus 1, quantity squared. And I will have on the bottom just a 1 squared. So here it is. It's u prime over 1 plus u squared. I could have just told you that, but I like to show it to you. If you didn't understand the derivation, that's okay. But let's go back to that original one that I wrote. Okay, so I'm going to do a little erasing here. I wonder if there's a way to get a clean sheet. Oh, no. That'll work. So what I want you to do right now is, let's write that in a big box. Let's put a box here. There's two things I really want you to have down by the end of these notes. Let's write the derivative with respect to x of arctan u, I just derived it, is u prime over 1 plus u squared. Okay, I'm going to put a little box here that I'm going to have you fill in later. So go ahead and draw that in your notes. We're not ready for it yet. We're just going to go practice a little bit with the arctan. So if y is equal to, let's use that arctan of 8x. And I say, what's y prime? The derivative of the arctan function. We do u prime over 1 plus u squared. That's it. The derivation was the hard part, and you don't have to derive it, but I like to show that to you. If I just had a naked x, what would that be? Suppose f of x was equal to just arctan x. Well, what would the derivative be? In this scenario, u is x. It is u prime, the derivative of x, over 1 plus x squared. How easy is that? So that's how we use that one. The next one I want to derive is arcsine. All right, so one more. We are going to figure out, and we'll put in this box, what the derivative with respect to x of arcsine of u is. Well, I'm going to do it the same way I did the last one. I'm going to say, well, I don't know what its derivative is. I'm looking for dy dx, so I'll let y equal arcsine of u. Unfortunately, I don't know the derivative of arcsine, so I can't take the derivative right now, but I can apply the sine function to the left and the sine, the inverse function of arcsine, to the right. Sine undoes arcsine. They're inverse operations. So I end up with the sine of y has to equal u. Now watch when I go draw my little right triangle here. My angle is y. Its sine, which is its opposite, over its hypotenuse is u. So opposite over hypotenuse. I'll find that missing third side by saying whatever it is, a squared plus b squared equals c squared. That means a squared is equal to 1 minus u squared. And equivalently, that missing question mark is the square root of 1 minus u squared. All right, square root of 1 minus u squared. So there we go. Now I'll take a derivative. So the derivative with respect to x on the left will equal the derivative with respect to x of the right. The derivative of sine x is cosine x, dx dx. The derivative of sine y is cosine y times dy dx. Let's call it y prime this time. That's going to equal du dx. Well, remember, my goal is to find y prime, the derivative of arcsine. So my y prime is going to equal, I'm going to have to erase my reference triangle here for you. My y prime is going to have to equal u prime over cosine y. But the problem is I need to have it as a function of u. That's what it started off as, was a function of u. I need to give its derivative in terms of u as well. So I erased my reference triangle. I'm going to throw it back on there. You should have it on your notes, right? We had a u and a 1 and a square root of 1 minus u squared. So I'll have u prime over the square root of 1 minus u squared, because cosine is adjacent. Here's my y, adjacent over hypotenuse. So just be the square root of 1 minus u squared. So this is u prime over. You'll notice they look very, very similar, correct? And all of them, no matter which one I did, whether it was cotangent, cosecant, secant, cosine, any of the 6 trig functions, their derivations, if I derived all 6 of them, I'd drive you nuts. So their derivations are all the same, and so they all end up with having this u over here that you take a derivative of. So u prime's always on the top, so that's going to be easy to memorize. In terms of the difference between arctan and arcsine, a couple years ago we came up with, you know what, a lot of times girls feel like they, not only girls I suppose, and boys, feel like they look prettier when they have a tan. So what we'll sometimes say is arctan is the prettier one. And if we were doing this in class, I'd say it's pretty for 2 reasons, and I'd make you repeat them several times. And that's where this distance learning is a little tricky, because I can't do that here. But arctan is prettier for 2 reasons. It has the prettier operator. We like to add more than we like to subtract. And it also doesn't have the root. So think tan, pretty, sine, ugly, and then think of what makes it prettier. It's a plus and it doesn't have a root. Sine has a minus and it has a root. So that's how you're going to memorize them. And it makes the derivative with respect to x of our cosine really easy, because the co-functions are all just negated. So whether it was cotangent or cosecant or cosine, it's just negative u prime over. And then it's the square root of 1 minus u squared. So even though you don't need to know cotangents, it would be negative u prime over 1 plus u squared. And that you could prove it to yourself by deriving them, but I'm not going to do that. So what am I going to do next? We are going to do a few examples like the ones that are going to be in Delta Math, and then you just have a Delta Math assignment for today. Should be pretty straightforward. Try not to use your notes. But here we go. I'm going to do 4 examples. The first one is f of x equals arcsine of u. In this scenario, I'm going to make u x to the 5th. So if I asked you what's f prime of x, which is what they'll do on Delta Math, you don't want to derive it. They all have u prime on the top. Arcsine is the uglier one. We feel pretty when we have a tan. It's uglier for 2 reasons. It's got the uglier operator and it's got a root. And then we just do 1 minus. Arctan would have been 1 plus. And then we do u squared. X to the 5th squared is x to the 10th. No need to rationalize your denominator. Did you hear that? No need to rationalize your denominator. All right? So, sorry. Lainey, are you listening to me? Yes? Okay, awesome. Lainey's always listening. Are you awake though, Lainey? That's the question. All right, so let's go back and do another one. It's as easy as that, right? So we'll do another one. What if f of x was arctan of just plain old x? Well, its derivative would be u prime 1 over 1 plus x squared. But I want to find its derivative at root 2 halves. So I do what I always do. I take the derivative. This is the inverse trig. They all have u prime on the top. In this scenario, u is x. The derivative of x with respect to x is 1. Over, now tangent's the prettier one for 2 reasons. It has a plus and no root. And then it's just 1 plus u squared. So now when I'm doing it at root 2 halves, I just plug it in. So I'd say f prime of root 2 tooths is equal to 1 over 1 plus root 2 over 2 squared, which would be 2/4 or 1/2. This is 1 over 3 halves. Delta Math's going to ask for it as simplified as possible. So if that was on Delta Math, you'd enter 2/3. 2 more to go. A lot of times these are combined with, and I have a feeling on your AP test there's going to be a lot of combo questions because they have to kill off the entire course in 45 minutes, which means some of the questions are going to be checking off a lot of boxes. So you probably wouldn't be asked to just flat out find the derivative of the arctan function, but they might combine it with maybe the formal definition of the derivative. Remember what that is. It's the limit as h approaches 0 of f of x plus h minus f of x, change in y, over change in x. This, I'm not going to show you again. I've showed you about 3 times why that is the derivative. It's the formal definition or the limit definition of the derivative of the function. Some of us are still thinking it's the function. It's not. It's the derivative of the function. So watch me apply that in a combo move with our new derivatives. The limit as h approaches 0 of arctan 2/5 plus h minus arctan 2/5 all over h. This is the formal definition of the derivative. I see the trigger, I see that f of x plus h, but remember this is the derivative of the function. So my function is arctan. The derivative is what I need. The derivative of arctan of x is 1 over 1 plus x squared. All right, so be careful. This is f of x. It's f of x plus h minus f of x. So this is the derivative of arctangent of x at 2/5. So the derivative of arctan, that's the prettier one for 2 reasons. It has a plus and it has no root. This is the expression for the derivative at 2/5. So you can see that x value in there. F of x plus h minus f of x all over h. So it'd be 1 over 1 plus 2/5 quantity squared. That's going to need to get cleaned up. So 1 over 1 plus 4/25. Get a common denominator, 25/25, which is 1 over 29/25, equivalently 25/29. So that's how the delta math is going to flow. There is one new version of the derivative in delta math that I actually did not teach you in our limit and derivative beginnings because it falls out when we do something called L'Hopital's rule. But due to changed circumstances here, I'm doing stuff a little bit out of order. So I'm going to show you what the alternative form of the definition of the derivative says. It says that the derivative at a specific spot. So graphically what that would mean is I'm at A. A might be 2. The derivative here at 2 can be found by doing a limit as x approaches a. So what that means is I have some other point over here. This is a f of a. And this is now x f of x. In the other form of the definition of the derivative, the first point was x f of x, and the next one was x plus h f of x plus h. So if I were to draw the secant line and have x approach a, that point would be getting closer and closer and closer, so that secant line would approach and eventually land on the tangent line. And remember, for a secant line slope, that's just algebra 1. It's change in y over change in x. So this is the formal definition of the derivative of f of x at a. Now, I'm just going to give you a little preamble what L'Hopital's rule says. It says something very basic. Its proof is quite complicated. But L'Hopital's rule says that when you get, and that's going to be our in a couple days, but I'm just going to give you a little preview of why I usually don't teach this form. Like the BC kids don't approach it this way. What they do is they say, well, I'm going to take my limit as x approaches a, which means I put an a here. And you'll notice on the top, I get f of a minus f of a over a minus a. I get 0 over 0. What L'Hopital's rule says is that when you get a limit that's 0 over 0, you can take the derivative of the top. So in this case, I'd have f prime of x, and f of a is a constant, so that'd be minus 0 over the derivative of x, which is 1, minus the derivative of a, which is a constant, which is also 0. So you'll notice I get f prime of a. So let me show you how you're going to apply that. All right, giving you a little too much theory here, but that's okay. It's good for you. It'd make you grow hair on your chest, as my dad used to say. So since I'm going to take the limit as x approaches a, 2/5. It's not h approaches 0. It's x approaches a of some function, arctan of x, some function, minus that function, arctan, oops, sorry, I wrote tan inverse, so I might as well stick with it. Tan inverse of, so this is my f of x, tan inverse of x, minus it evaluated someplace, I'm going to say 2/5, over x minus that is actually equal to the derivative there. All right, it's the slope of the secant line between the 2 points. So what I do is I say, well, who's my function? Arctan. What's its derivative? Ooh, it's the pretty one. It's u prime. Remember, here's my function. Here's my function. It's u prime over 1 plus u squared. So in this case, it'd be x squared. But this is being evaluated at 2/5. So what I do is I say it's 1 over 1 plus 2/5 quantity squared. And then I'd clean that up. I'd have 1 plus 4/25. I would have 25/25, 29/25, and then I'd have to flip her on over, but you can clean that up. That's just arithmetic. So I'm done. What you need to do is the delta math, and there's 10 of them, and I put a half-point penalty in there, so you have to get 2 wrong for it to knock you down. Thank you, Miss LaRune. You're welcome. Let's see, Lindsay, right? So goodbye, all you guys. I hope that went well. I'll know when I look at the delta math whether I went too fast. I can see the stats on that. So you need to submit these notes as an assignment, and then the second part of your assignment will be the delta math. So 10-point assignment, 5 for notes, and 5 for completing the delta math. Have a good one, guys. I hope all's going well. Feel free to send me any questions you have. Over and out, and peace out. LaRue's out.